Hello everyone, my name is Andrew Marin, and thank you for stopping by my poster entitled Occlusion of a Dynamic Visual Object Influences Visual Expectations of an Ensuing Sound. And so to start, seeing a moving visual object can help generate expectations about accompanying sounds and can facilitate early auditory processing of sounds that are associated with the object. At times, a moving object may become occluded, and it is unclear to what extent such disruptions to the visual input affect expectations about the subsequent sounds. And so for this study, we asked, does a moving visual object that is occluded trigger expectations about a sound associated with the object? In this study, we plan to measure slow wave activity in the EEG as a neural marker of expectation. In past ERP research has shown a fully visible moving object, and one that enters and exits occlusion elicits late positive going slow wave activity over occipital areas of the brain. Conversely, in cases of cognitive expectations, the brain generates negative activity over frontal central regions of the brain. In considering this, we hypothesized that if the occlusion of a visual object generates implicit expectations about a subsequent sound, this will result in differences in the late slow wave activity compared to non-occluded visual input. Onto the methods, where college-aged neurotypical adults participated in 2 experiments. And below is a single trial depiction for both experiments, and this interval here contains the primary task, where participants viewed a ball that moved to the left or to the right, and the moment the visual object reached the edge of the display, a bounce sound occurred. And we assessed the late slow wave activity elicited by a moving visual object within the red occipital region seen here using high-density EEG for both experiments. I'll now present the 3 sensory conditions used for experiment 1 with the event epoch drawn below, and each condition was presented 104 times. The audiovisual full condition contained unobstructed continuous motion of the ball moving toward and bouncing off the opposite edge, which elicited a synchronous bounce sound at the point of collision as denoted by the yellow star. The ball then reversed back to its origin and the stimuli subsequently terminated. For the second condition, participants were briefly shown visual and motion cues provided by the ball in its motion, but the ball moved behind an invisible slit in the display when it approached the halfway point at approximately 600 milliseconds. By the time the ball reached the opposite boundary, it was invisible, but a bounce sound occurred during expected contact. The invisible ball then reversed, moving back to its origin, and reappeared before the stimuli terminated. And lastly, we provided an audio-only condition which contained a bounce sound but no continuous motion of the ball. I'll now present the grand average ERPs plotted positive up for experiment 1 for 19 adults. On the y-axis we have amplitude, and the x we have time in milliseconds, and these ERPs reflect the main effective sensory condition over occipital electrode sites. The blue star denotes when the visual object started its occlusion, and our primary dependent measure was the mean amplitude from this point within 3 equally spaced 200 millisecond time windows. And here are the results of that ANOVA, where I plotted the significant condition time point interaction to the left, and the y-axis reflects the mean amplitude of the slow wave response, and the x-axis presents each equally spaced 200 millisecond time window. And here you can clearly see what's demonstrated in the ERP figure is that the occlusion of a dynamic visual object elicited a negative slow wave compared to fully visible visual input. Interestingly, the scalp distribution of the difference in slow wave activity between the half occluded and audiovisual full condition was particularly most negative over occipital regions. And so considering these data, we asked ourselves, would the amount of visual information generate different patterns of slow wave negativity? And so a second experiment was devised where we systematically varied the amount of time the ball spent under occlusion. And as with before, I'll present the 4 conditions for experiment 2. The audiovisual full was the same as experiment 1, and in the conditions presented below, we manipulated the amount of time the ball spent under occlusion. So for example, in our least occluded condition, the 2/3, the ball underwent occlusion at 900 milliseconds. And we hypothesized that a reduction in the slow wave response would be seen here shortly after occlusion. And for the most occluded condition, the ball started its occlusion at 300 milliseconds, and a reduction in the slow wave response should be seen here at this early occlusion point. Importantly, each condition in this experiment contained a synchronous bounce sound. I'll now present the grand average ERPs for experiment 2 for 17 adults, and each color-coded star denotes when the visual object could start its occlusion for each condition, and we collected the mean amplitude slow wave response from each occlusion point with the hypothesis that a slow wave reduction should arise shortly after each condition's occlusion point. I plotted here the non-significant condition time point interaction to the left for consistency, and to give the most representative view of the overall findings. And here, the occlusion of a dynamic visual object resulted in a negative slow wave compared to fully visible visual input, regardless of the amount of occlusion. And as with experiment 1, the scalp distribution of the difference in slow wave activity between the average of the three audiovisual occluded conditions and the non-occluded condition showed a similar topography. In sum, our analyses focused on a late slow wave occipital ERP component, which has previously been associated with the buildup of sensory expectations before the onset of a sound. We found that visual occlusion resulted in slow wave negativity over visual regions of the brain compared to non-occluded visual input, seemingly independently of the amount of occlusion. Overall, these results may suggest occlusion of a dynamic visual object reduces visual activity compared to non-occluded visual input. And to close, previous research has found that a moving object results in the desynchronization of alpha activity before the visual object enters and exits occlusion. Future research will quantify occipital alpha in response to a dynamic visual object that undergoes various amounts of visual occlusion. And lastly, I'd like to thank all the awesome undergraduates that participated and my advisor Leslie Carver and fellow collaborator Viola Stormer, and you for listening. Thank you very much.